Today we're going to be covering Lab 1, Constant Velocity, in which we use Newton's second law to build a model predicting the change of position of an object over a period of time, given that its velocity remains constant, and compare our model to a recording of a real-world object moving at constant speed in the same direction. Now Newton's second law states that the difference, or the change, in velocity initial and velocity final is equal to the net force divided by the mass times the change in time. For our model, we're going to assume that the net force, Fnet, is equal to 0 because that would make the entire right side of the equation equal to 0 and make the initial and final velocities equal to each other. Now, in an experimental setting, it's nearly impossible to create a zero net force environment for the system, and this is what's going to cause the discrepancies between our experimental data and the data from our model that we're going to see later. Here we're using Tracker to map the change in x position of a tennis ball over time. The slope is of course positive with the ball moving from left to right in the x positive direction with relation to the axis, the origin of which is placed at the center of the ball at its starting position. The diameter of the tennis ball, 0.068 meters, is used as a reference, and the position of the ball is recorded every 30th of a second. Now, in order to make our computational model, we need four components. The first being the initial position, which as we've discussed, we've made the origin. The second being initial velocity, which, since we can't observe instantaneous velocity, we obtain by observing the change in position over time of our first 2 points. And we can get this from our data, and we end up with a vector 0.767, 0.03210 meters per second. And we can essentially ignore the y and z values since our model is only going to be showing the function of x position over time. So third, we need the time window, which is 1.435 seconds we get from the last t value. And last, we need delta t, which should be a small value since we're dealing with Newton's law, but doesn't have to equal the frame rate of the video as long as the overall time window matches. And up here we record the mass of the tennis ball, which would be important if we were not assuming zero net force, but since we are, velocity will remain constant regardless, according to Newton's second law. Let's compare the data of our experiment with our model. When we look at the data side by side, we see the model predicts the motion of the ball well initially, but becomes very inaccurate later in the time interval. This can be attributed to the fact that one of our assumptions, zero net force, was not maintained constantly throughout the time interval. This is likely because frictional forces in the negative x direction were greater than the forces pushing the system in the positive x direction later in the interval. Still, even if modifications were made to better simulate a zero net force system, it is nearly impossible to maintain a truly zero net force for the entire time interval because there are many forces acting on a system at once, in many directions, and accounting for all of them is extremely difficult. However, thanks to Newton's law, we don't have to add up all the forces on a system to be able to say whether the net force is zero. If the velocity remains constant for the duration of the specified time interval, we know that the net force during that time interval was zero. Now, with this in mind, a better model for this experiment would have taken into account the non-zero net force in the negative x directions, causing the observed deceleration. One more thing to note. The positive x direction was determined based solely on our decision of how to orient the axis. We could have just as easily made right to left the positive x direction, in which case the magnitude of the position vectors for both the model and the experiment would not change, but the x component of the position vectors would become negative with respect to the origin, and the data that you see here would be mirrored over the x-axis. That concludes our Lab 1 overview.